Is this better? Okay, cool. Hi everyone, thank you for being here this morning. I'm Anna. I'm a postdoctoral fellow at the Santa Fe Institute in Santa Fe, New Mexico. I primarily work as a historian and philosopher of science and scientific images in particular. Today, though, I'm speaking on behalf of a team with me and a physicist, who's Dr. Erin Dinner, and many talented and patient software engineers, some of whom are in this room, like Julia. Thank you for being here. So if I do badly, they all go down with me. So my aim generally today is to report on progress that we've made in developing a tool that I lovingly call PicAxe. In a perfect world, somebody with no coding experience could give PicAxe a large corpus of PDF documents of variable time periods, cultures, and scan quality, and PicAxe would return PNG files of all the images in those documents. That includes things like photographs, diagrams, graphs, what I'm learning this week notoriously, tables. But the world isn't perfect, so let's begin. Okay, cool. I'll start by explaining why we've spent so much time and energy doing this and sort of unexpectedly. On the one hand, there's a growing interest in using computers to study images as called cultural artifacts, and especially in finding patterns in large corpora of images using machine learning. And if you're wondering if that work is good, it's getting there. You know, it's got to be not good before it's good. But a lot of research that analyzes large corpora of images with computers focuses on images from maybe like web pages or social media, and that's partially because scraping image data from those sources is relatively easy. But humanities researchers study cultural artifacts with text and images that were not born on computers, or once they're on computers, they're not easily scrapable. Consider artifacts like newspapers and textbooks and even cookbooks. I specifically study the images that appear in scientific journal articles and books. Some digital humanists study the evolution of scientific knowledge through textual discourse, and I'm sort of aiming to do similar things in my current position, but to study the evolution of scientific knowledge through image discourse, which requires extracting a lot of images generally. So to learn about patterns in such images using computers, it's usually helpful as a first step to just extract the images from their text image environment, which doesn't sound super complicated, but for large corpora, it ends up being that way. So in a world without, and sorry, all the titles are under that space. In a world without PicAxe, you have a few free options for extracting images from digital non-scrapable text image environments. First, you have manual tools, which probably most of us have used unethically in our lifetimes. This includes tools like screenshot and snipping and crop functions that are built onto your computers, as well as functionally similar crop and marquee tools in popular image processing software. So if you've got like 60 or fewer images to extract, I think manual tools are a really good option for you. And if you have anything more than 60, manual image extraction becomes time consuming. It becomes a lot harder to keep your data and metadata organized. And most importantly, if you have more than 60 images to extract, you're going to hate your life. And I don't want you to hate your life. So as far as pre-built and free is the keyword, automatical unsupervised image extractors, there are a few tools that have theoretically image extraction functionality, and these include PDF Plumber and PDF, which are wonderful tools. But you might be wondering if they're good options, and me being up here might signal to you that no, generally they're not good options for this particular task, and there's a few reasons for that. There is the practical barrier of reading and implementing source code, and I recognize that in this crowd particularly, that those particular barriers aren't super intimidating, but please consider all the humanists who are not proficient coders and or suffer from malaise like me. So more important to barrier than access still is that these tools probably won't give you very good extraction results for a corpus of text image documents, and that's one, partially because they weren't built for that, and two, they haven't taken into account the diversity of image encoding in PDFs because they weren't built for that. So I'll explain a little bit what that means. PDFs are diverse in how they encode image data, and it partially depends upon when and how they were produced. So documents that predate the existence of computers, like the one on your left, exist digitally as scans or photographs of hard copies. The age and method of digital preservation influences the quality of the text and image data in these PDFs, and that includes like quality as in how good it is, and quality as in like the syntax of it once it's on a computer. And so the data on those images can appear warped or tilted or incomplete or with aberrations, and those are extraction challenges in themselves. And then newer text image documents, like the one on your right, are often generated and spread as born digital PDFs. And in those kinds of PDFs, images are usually embedded as things called X objects, if you ever put it into PDF readers. The automatic image extraction tools that I mentioned on the last slide usually depend on the encoding of images as X objects in PDFs to extract them, because it can recognize that this object is different than text and pull it out. But there are some problems with both of these things. On the one hand, on the older scan side, rarely are images embedded as X objects unless somebody goes in later and makes that modification. And so if you give it to any of the extractors that exist already, it just makes a copy of the entire page of the PDF. It gives you a PNG of it and says, you're welcome, and that's generally not what you want. But extracting images from foreign digital PDFs you think would be relatively straightforward, but you might be disgusted to learn, as I was, that people are, oh, and you can't see it behind this thing. Can I move this? People are encoding their images as X objects as like individual vectors. So if you use these tools, it's going to pull all these weird shapes out at you, which means you have a lot to do in terms of fixing that if you want to use it for born digital PDFs, and that's usually not your goal. And so, as many of you are aware, document layout and page segmentation are sort of hot topics in machine learning in general, but we as a group were sort of hesitant to start with those methods, partially because the tools that were accessible to us were trained on stylistically homogeneous born digital documents. And I wanted a tool that worked on older things, generally as a historian, and also on syntactically diverse corpora. We wanted to try to build a tool that would cover the broadest range of corpora that somebody could bring to it with minimal sort of training. So in summary, sorry, this thing is huge. Can I get this small? Nice. Okay. So in summary, we designed PicAxe to manage sort of stylistically or syntactically diverse text image environments, to manage the variability and the extractability of image data, inherent to a PDF file format, and to, most importantly, be accessible to humanities researchers with no coding experience. So let's go through what we have. This is our software architecture. In a nutshell, it has some images to help illustrate how this works. You give it a PDF and a PDF page, might look something like that. That's from an older microbiology text. It converts the PDF pages to binary PNGs, which is an image file. And then once it's a binary, it's easier to use the rest of the architecture. We rely on PyTesseract, which is trained code, to do OCR. Once it does the OCR, we have it eliminate the text fully, and that's what you see sort of in this no text PNG in the middle there. We use a combination of OC thresholding and contour detection to capture what is left on the PNGs after the text that it can recognize has been eliminated. We have some rules that eliminate odd contours, so like things that are super tiny that probably wouldn't make sense to extract as an image, or things with maybe like really weird size ratios. And then we use a dilation to combine contours that are close together, and so you can see something like the bottom of this fourth image there. If the contour detection sort of detects two halves of an image that are separate, if they're sufficiently close by our rules, then it will know to combine those fully, and then it will extract the full image from the original PDF. This was like our sort of scrappiest, lowest number of things to make it work well. And that's currently how it mostly works. So we're playing some modifications that I'll discuss later. Cool. So I'll show you some results. We have tested the tool on multiple corpora that had like anywhere from 300 to 400 PDFs in it, which produced somewhere from like 2,500 images to maybe 4,000 images, but this is just one corpus that we're gonna look at today. There are 308 publications in that corpus. The year range was 1929 to 1974. The document types were journal articles and book chapters. And then the image types within those included photographs, photomicrographs. If you're not a microbiologist, that's just a photograph made with the aid of a microscope. Diagrams, graphs, and tables. That corpus sort of represents an early history of microbial biofilm concept in the 20th century, and that's what I did my dissertation on, which is why I had this whole corpus manually extracted because of the work that I did for that without having a tool like this. And so when you do the extraction manually or by hand, you get around 2,400 images, and if you're trying your best, you can extract like 60 images per hour. Usually, we're not our best. And then we have PicAxe, which runs mainly as an OCR with Tesseract. It extracts around 3,100 images, which is quite a few more, but it extracts 516 an hour, and you didn't have to do it yourself, which is very nice. When we wanted to characterize sort of the quality of the results, we felt that just looking at whole page results didn't really tell us much about the kinds of mistakes that it was making. So we sort of broken out the analysis into 3 categories. So I'll sort of orient you to the categories. There's this blue section, which is when PicAxe extracted the same number of images in a single PDF as a manual extractor would have. So that would be hopefully like perfect extraction that matches a manual extractor. There is instances where it extracted fewer images than the manual extractor, and that's bad because it means it just totally missed something. And then there's cases where, and this was almost half of the cases, where it extracts more images than a manual extractor would extract. And before we had run these tests, my worry was that it would miss a bunch of stuff, and that wasn't as much of the case as I thought, so that was good. That I guess everyone knows what precision and recall is, because I've seen it so many times this week, but I had not personally looked at this concept before doing this project, so that table is mostly for me. We have some pretty good results for precision and recall for each of the categories. Obviously, for the precision of cases where it extracts more images than a manual extractor, the precision is lower because there's a lot of false positives. And then for recall, the recall of cases where it extracts fewer images than a manual extractor is a little bit lower, and that makes sense because there are more false negatives, but generally we're happy with the recall. So I think this may be the most valuable slide here. I can't do that, but it says these are the most common problems these are the most common features of PDFs that gave the code issues. And so I'll orient you to this. We have them sort of on this spectrum of acceptable to unacceptable. The reason it's on a spectrum is because of the heterogeneous nature of the documents we gave it, it was hard to sort of predict what the main issues would be for any given corpus. But it seems like some things we could fix and get a lot of improvement in performance, and we wouldn't break everything. And some things we could fix and we would get somewhat improvement in performance, but it would probably break everything. And so that's sort of how we decided where these things are going. On the left, for acceptable features that prevented extraction, you have grouping rules. So you'll see you have like a figure here that was extracted from a document, and then you have this, which is just sort of a blown up version of that, and it extracts it separately. It's probably because our spacing rules didn't encompass it to have it extracted that entire image, or it was far enough apart that it recognized it as its own section. There are many cases where a manual extractor could also make decisions that meant that things were split up. There's lots of figures that have like A, B, C, D, whatever, and so you often have to make decisions as a manual extractor if you want to keep those things together, or you want to separate them, and you think that would be clear cut, but it's not always. So grouping rules seem like something that we could not worry too much about not being perfect compared to a manual extractor, because even a manual extractor might have variability. The next thing that caused a lot of issues were dots and equations, but what we're calling text symbols. So these are things that Tesseract could potentially read as text, or it could potentially not read as text, depending on maybe the syntax of the document. Again, there's cases like this, where like, okay, yeah, sure, it's not text, it's not exactly what we wanted, but it will really depend on the corpus of the user, so we're not as worried about those things. There's probably some fixes for equations if you care about equations, but we don't have time to talk about that today. The next thing is scan aberrations, and that's common with older documents that were scanned or photographed onto a computer because they existed as materials before. These things seemed less acceptable, and often these aberrations are like these little scan dots, and it would pull like groups of dots, and it's like, you don't want that. It's not the worst thing in the world because a manual, like a user should probably go through and check their results, and they would see that and they'd be like, that's probably not what I want, and they can delete that, but there are probably ways to get rid of that. And the worst thing for performance generally were these orders from scans and these sort of like long like division lines, which again makes sense, they're not text, but they really mess up extraction, and we don't want them. And there's probably easy rules to write to eliminate those things before we perform extraction. That would improve performance a lot. And what's exciting about this is that these were generally the problems for all the corpora we've tested. So we think we can get really good performance for broad corpora by just dealing with these things. Cool. Oh, I'm done. Okay, sure. Modifications, we can talk about that. This is what we're doing next. We're going to test more corpora. If you have some you're interested in, please give them to us. We'd like to improve the speed. We'd like to have metadata generated alongside the images, because right now we do it by hand. And then we'd like to integrate it into Files, which is Julia's project that does OCR, large-scale OCR and corpora text documents. And then you can get text and images if you want. And those are just things we were going to do to solve our biggest issues with. That's it.